Hi, everyone, and welcome to the first episode of Lunch and Learn with Hudson and Thames. We're doing upskilling at Hudson and Thames, and as a part of it, we're finding various pieces on programming in Python, quantitative finance, and finance in general. And we thought that it's useful to share some of the ideas and information with you if you're interested in practicing quantitative finance, or if you're just an enthusiast. We're just trying to pack densely the useful information that we find. And the core idea of Lunch and Learn is essentially to lunch and learn. So you would maybe watch this episode while you're having lunch. We're planning to make them from 15 to 25 minutes each. And yep, just for your information. The first few episodes will be related to programming in Python and this specific book, High Performance Python by Gorelick and Ozsvald, second edition. Before I start, I highly encourage you to check the original book because what I'm covering is a very dense, maybe part of it. So I'm covering maybe 30% of the original chapter 2. And for many more insights, use cases, and to better understand how the tools that I'm covering today work, please go and get the original book. Today, in the episode 1, we're covering chapter 2 on profiling and finding bottlenecks in your Python code. So a quick note about me. Hi, my name is Illya Barziy. I'm Quant Research Team Lead at Hudson and Thames. If you'd like to discuss any parts of the Lunch and Learn sessions of this particular presentation, feel free to reach out to me via these social links. Also, the link to the slides that I'm presenting right now is available under the video, so feel free to. Also, if you have any questions, please feel free to leave them in the comment section. I'll be happy to answer those. Okay, so the contents today are as following. We'll briefly understand what the profiling is and why you might be interested in using it. Introduce the Julia set is the specific set that the authors used in the original book to describe some of the concepts here and why this set is interesting. Simple approaches to timing, how to use cProfile module for profiling, line-by-line measurements of your CPU usage and memory usage, then diagnosing memory usage, inspecting processes Python, examining CPython bytecode, and finally some notes on good practices in profiling, optimizing your code, and unit testing. All right, so profiling tools overview. What is profiling? And it's very well described in the original book, saying that profiling lets us find bottlenecks so we can do the least amount of work to get the biggest practical performance gain. Essentially, you want to know where would you want to optimize your code for it to run faster, but also to spend your time in the most efficient way and to make your code most efficient possible, with your constraints being time constraints and knowledge constraints. And essentially any resource can be profiled as mentioned in the book. And in general, this can be CPU and memory, these two particular pieces that we're going to be covering in today's talk, but also you can check network bandwidth and disk IO if your specific tools are related on those and you want to profile them. However, they're not covered explicitly in this chapter and this talk. All right, so the tools that we're covering is timeit and time modules, cProfile module, external packages as line profiler, memory profiler, PySpy, also checking your bytecode in CPython with the this module, integrated module, and also good practices on integrating unit tests while you're profiling. All right, so the Julia set. The authors used this problem to explain the concepts in the chapter, and I just decided to share this with you because it's a rather interesting problem. It's a CPU-bound problem for generating a fractal sequence, a complex output image, and it's named after Gaston Julia. This is an example of an imagery output that you might see. So the core idea here is that you would pick a point in a complex space, C, so its part is a real value and its part is an imaginary value, and you would then run an iterative process of taking a square of Z, previous value of the function plus that C, and you at each iteration check if it's smaller than 2 or not. And this space right here, you have the x-axis and the y-axis, and this corresponds to the real and the imaginary part. So for each pixel, you have a bit different starting value of the function and a bit different progression of the function. And essentially, once it's higher than 2, you would record the number of such iterations it took for it to be higher than 2 as the pixel value. And so dark parts here is where maybe from the first or 0th iteration, we saw that the value is already higher than 2. And sometimes it takes much longer to run. And this white zones, it's where it capped out at 10,000 iterations, still not reaching the value of 2. And this problem is not that trivial, because you cannot say beforehand, taking a square value of a point in complex space and then adding a piece to it, at which iteration it will exceed this value. So it can be repeating itself over n iterations with slight differences, but then at one iteration it will jump and be higher than 2. So a complex problem, but a good, interesting piece of it is that it's highly parallel. So one point doesn't depend on the other point in terms of calculation. So if you're also trying to play around with vectorization, this is a good idea to use this set to just try around. All right, now to the actual pieces of profiling. The first thing that we're looking at is timing and a few things that can be used. So it's the time module, a built-in Python module, and you would essentially print statements of when you started timer and ended timer. It's okay for very quick checks, and I assume you're using this already. But if you want to be a bit more precise, it's better to write a decorator that would take your function as the input, and then outside of the function calculate the time it took to run your function. Essentially, it works. You would import the time module, then you would call the time method at the beginning. You would run your thing, and then you would essentially capture the end of the time. And then those difference would be the seconds it took to run your script. The next thing, which is a bit more not scientific, but precise, is in this case, you're running only one iteration of it, right? So you're checking how long it took once to run your method. You can also do it maybe in a loop to calculate multiple times, but there is a better way to do it, is to use the timeit module or the magic timeit if you're using an IPython console or if you're working in a Jupyter notebook. And so from the command line, you would call it as Python module timeit with the N and R key, stating the number of loops and the number of repetitions of your code, and then your function with arguments. Or in IPython console, you can call it with timeit and your function. The cool thing about this, it will run multiple times. And in case of the first thing, so in the command line run, it will give you the best result out of all runs. And in IPython console, so right here, it will give you the output of mean time that it took for all the repetitions to run, and also the standard deviation. And so this, as you understood, cannot be compared directly. So you're comparing minimum value it took to run to the average time it took to run. But well, if you're using each one of them individually, it's an okay tool. It's a very good tool, actually. So I guess this is a good balance to capture the time it takes to run your function. Also, in Unix-like systems, you can just use the system time command with user bin time p python and your code.py. And in this case, you'll get just a system overview of how long it took for your code to run. It may be useful if your code is heavy on imports, exports, and maybe there's a lot of stuff going on. And it's much better to run it as a whole script rather than just a single function. Cool, let's proceed. And the next thing is the cProfile module. And cProfile is a profiling tool in the standard library, which hooks to the virtual machine of CPython and measures the time it takes to run each function. So whereas in the previous ones, we just checked how long it takes to run the entire piece of code, here it measures how long it took to run each function. It adds a greater overhead to your calculation times, but it's very good for finding insights. And in terms of overhead, you might expect like 50% increase in the calculation time. You would call it very easily from your console with Python, mem, module, cProfile, and S cumulative flag, standing for cumulative time spent inside each function, and then your code.py. Maybe you want a bit more control over the output or analyze it later, then you can use and just run your output in the profile.stats file. And this would be Python, m, cProfile, output to profile stats key right here and your code part right here. Later in Python, you can import the pstats package and then import your statistics and just get a more detailed output. You can also check callers, callees, and we'll just see in a minute why it's useful. Also, before I proceed, it's a very good idea for you to first make a hypothesis of why things don't work that quickly as you expect them to, and only then use the profiler. This way, authors suggest that you'll get an intuition of the parts of the code that don't operate the correct way. And with time, you'll get a bit more intuition on how to write the better code instead of just kind of checking what's wrong and just fixing it. And then next time, not understanding again what's going wrong. Cool. So this is the standard cProfile cumulative function output. We see the total number of function calls. We can see the total time it took to run the code. In this case, 12 seconds. What's useful about it is that you can see the number of calls for each function. And you can see that in this particular code example, the highest number of calls was for the apps method in Python, and also a method for appending list objects. And you can also see the cumulative time for the apps was 3 seconds out of 12 seconds. So it's a pretty high percentage of time was spent doing this part right here. You can also, with a bit deeper inspection, check the callees. In this case, is just seeing which function called which other function. You'll see the same values right here. So with the apps value, you can see the same cumulative time, but you'll just be able to see which function called them. So if you have, for example, this apps present 5 times in your function or in subfunctions, you'll see which exact subfunction takes the longest run. But you can freely experiment around it and see what works better for you. Now, we can see how to check which subfunction took the longest time to run and which method took the longest time to run, but it doesn't specifically represent on which line this code was running. And this is a great tool for you to use. According to one of the authors, Ozsvald, this is the strongest tool for identifying CPU-bound problems in your code. I tried it, and I do agree that it's a very useful tool, and it's, in my opinion, maybe even easier to use than the cProfiler. This tool, however, is not a standard tool in Python, so you would want to install it from PyPy with pip install line profiler. Then, and remember this, please, you should use a decorator just to mark your chosen function. Otherwise, it just won't work. And once you marked and once you entered your calculations inside of the same script, you would run the kernprof script and execute your code and see the CPU time to run each line. So it's kernprof LV keys. L stands for line-by-line profiling and V for verbose output of your code. And also, before we proceed, do note that this module adds a substantial amount to your runtime, whereas the cProfile added maybe 50%. This thing can take 6 times longer to run your code, maybe up to 10 times longer. So it's still not an overnight run, but do expect it to take some time to just gather all the calculations and give you the good output. This is how the output looks, and you can see that the time rose to 82 seconds from 12 seconds that we saw in cProfiler on the similar method right here. But what's cool about it is you can actually line by line see which line took the most percentage of time to run. And we can still see that the apps calculation and check here takes quite a big percentage of time, but also we can expect that these check takes 18% of time. These values right here take quite some time to run, and also the number of heads of this specific function. This specific line. A bit more verbose, better for you to understand and better to understand the exact pieces that you should patch maybe. But if you also see that you already boiled down to very basic Python methods and there is nothing better you can use, you may consider to use the type specialization and maybe go deeper into Python to optimize your code even further, just because of the overhead that Python adds to basic methods. Okay, next, diagnosing memory usage. And similar to line profiler, there is a memory profiler package, and it's also an external module, but giving you an increments of memory usage on a line-by-line basis. So you would install it via pip. Again, pip install memory profiler. You would use the exact same decorator, which is a big pro. So essentially you can decorate your one method and then use at the same time line profiler and memory profiler. Then you would call memory profiler from your console with Python m module memory profiler and your code.py. These results can also be plotted if you wish, but do keep in mind that it adds a very big overhead to your run times, up to 100 times slower your code may run. And in this case, you might want to, if you have a big code chunk, leave it overnight just to check the results in the morning. There are also simpler ways to do this with maybe the inbuilt Mehmet measurement. You can use it as a magic and at Mehmet your function arguments if you're using NIPython or you're working in a Jupyter notebook. And before we proceed with memory usage, it's not as clear in the understanding of authors as far as I understood, and also in my opinion, for a few things. So first, yes, obviously your goal may be to minimize the RAM used, but also you want to ask yourself, because there's kind of an exchange between the memory usage and caching some things to make the CPU run faster. So do you want to use maybe more RAM, but save a few CPU cycles by caching? That's a thing to ask yourself and just to measure and iterate over. Plus, some of these results can be a bit harder to interpret due to garbage collection not being instantaneous in Python. And so you might see in some places changes in memory usage that are maybe harder to interpret. But this is how, in any case, the memory profiler output looks like. And what you can see here is the usage of, so the memory usage and the increments here. And we can use that see that right here. For example, this line of creating a list output added an extra 7.6 megabytes to the memory usage. Also worth noting that in this case, it's not that so the data in this variable actually is 7.6 megabytes. It's just the allocated space is 7.6 megabytes because Python over allocates memory for lists. So you should be also aware of it. And also we can see a small increment of 0.2 megabytes in this iteration loop right here. Cool. You want to maybe inspect processes because this doesn't add any overhead, but still allows you to measure various things. For this, authors advise you to use the PySpy module. It may inspect already running Python processes or run new processes and inspect them from the start. And it does not have any or very little impact on the runtime. This tool, you want to install it also from pip with pip install PySpy. If you know your process ID, so your Python code running and you know the process ID in Unix-like systems, you would go sudo environment and then PySpy and give it the process ID to just check the terminal-like output of the way your process runs. Or you can run the process from the start without the PID. And in this case, you would call the module PySpy. This can be used for visual output. So in this case, we're outputting the flame chart in profile.svg file with Python and your code.py. And authors state that this tool is actually very useful in environments with long-running processes or maybe complicated installation requirements where it's much harder to use line profilers and cProfiler. Cool, this is how the output looks here. So this is the terminal-like output if you know the process ID. And this is how the output for the flame chart looks if you just run it from the start. Last but not least here is examining CPython bytecode. And why would you want to do this? It's having an understanding of how your code runs, so how your higher level Python code actually gets decomposed into bytecode and run, lets you to understand why one styles of programming are better than the others. The authors advise you to use the this module used in Python, and this is essentially showing you the bytecode used in CPython virtual machine. You would just import this and then use this.this on your function. As for example, here this.this and then on this function right here. The output is maybe not visually pleasant, but it's easy to interpret if you look at it for a bit. And so essentially I have 6 columns. One is contain line numbers that relate to the original file. The second one is the symbols that relate to jumping pointers anywhere else in the code. And the third line is the operation address. Then the fourth is the operation name. The fifth is the parameters for the operation, and the sixth is the annotations to help line up the bytecode with the original Python parameters right here. Now let's look at why it's useful. We have two code examples, code A and code B, that do the same thing. So they're defined as functions, and here we are given the upper parameter, in this case 1 million, and we're just summing the range of upper parameter. Essentially, we're just summing up values up from 0 to the upper value and just getting the output. You can also, so this is kind of a maybe more Pythonic way to look at the problem. A bit more C-like way would probably to do something like this, is to write the fn expressive with the same input parameter. Then you would then you would have the total variable, and you would iterate over the range, and on each iteration you would be adding a value to the total, and then you would output this total value. The logic is a bit the logic of what we're doing is the same, but the way it's done is very different. And you can also see this in the speed comparison here, whereas code A took 18 milliseconds on average from 7 runs and 100 loops, with a bit of a change in standard deviation. The code B actually took 52 milliseconds, which is more than about 2.5 times bigger, longer. Not that cool, and a hint of why it's happening and why one style is better to use in Python than the other, you would allow to understand this maybe looking at the bytecode. So this is the bytecode for code A, and essentially what's happening is we're loading global functions sum and range, then we're loading the parameter upper, and then we're just calling functions 1 and 2, and then we're returning the value. In the case of code B, and the bytecode looks a bit more complex. With a bit of time, you can maybe jump into it and understand what's going on deeper level. But just looking from it, it's not that native to Python and much harder for the later CPython to calculate this. And this is why the exact overhead is 2.5. So the runtime is 2.5 times higher. Cool. And now finally, a few notes and few comments on how to do your profiling and optimizing correctly and on the unit testing. First, it's always a good idea to use unit tests in your code and to continue testing them during the optimization process. One of the authors agreed, and it's a funny story from the book, that one time he was optimizing a piece of code and for simplicity's sake, he disabled the unit testing just to find out later during the day that he gained a very good performance boost, but he broke the original algorithm, which means that all the boost is actually non-usable. All the people do mistakes. Please do run unit tests alongside of your optimization just to keep your sanity. An additional thing is to use the coverage tool, which will exactly tell you which of your lines are exercised during the unit tests. And this will ensure that you're testing the same code that you're about to optimize. By which I mean, for example, you have a class with 3 methods, out of which only 2 you're using in the unit test, and you're optimizing the third one. Yeah, doesn't quite work. We at Hudson and Thames are using both unit tests and the coverage tools. They're easy actually to use, to interpret, and to add to your workflow. So even if you're not doing profiling, do use unit tests and coverage. The next thing is you might want to check the book for a no-OP profile decorator to make the line profiler and memory profiler actually being compatible with your unit tests. You want to make sure that your machine operates as a constant setting when you're optimizing the code or profiling it, because some side processes as may be running, Docker containers may decrease the CPU available for you to use, and on one iterations you'll see higher performance, and on another iteration you see lower performance. You want to, if you're optimizing on a laptop, always use an AC power, because the performance may decrease if you're on a battery usage. You want to run multiple experiments and etc. You want to, if you're using Intel processors, disable the turbo boost, because on first few iterations you'll see the better CPU clocks, and on later iterations you'll see lower CPU clocks. And there is actually a whole part of the chapter dedicated to a few advices on how you make your system run at a constant setting. As I mentioned previously, you want to make hypotheses and test them with the above tools to first develop an intuition of what may be going wrong with your code or which parts of it are slow or not, and only then check the profiling tools to confirm or just check your hypothesis and learn from it. And finally, you want to use a source control tool, so Git or other source control tools while you're profiling and optimizing your code, just to preserve your sanity and not to first fix something and then with next iterations break it and not being able to come back. As authors say, branching is cheap and to just preserve your sanity. All right, and this is about it for today's Lunch and Learn. Here, the reference section is just the book by Gorelick and Ozsvald for High Performance Python. I highly advise you to check the original chapter 2. Again, as I said, I only covered about 30% of what's being in there, and we're not jumping very deep into understanding how each tool works. Thank you very much for your attention. I hope that you found Lunch and Learn concept interesting. I invite you to the next sessions, and the next one will be happening is Valeria talking about data structures in Python and how they're different, why you should understand how they work under the hood. Thank you for your attention. I hope you have a good day. If you have any questions, reach out to me, and cheers.